Hi guys, David here. So for my science update today, I want to start off with this article from Science Daily, and it's called Habitability Limited by Its Small Size, Isotope Study Suggests. And so the summary is that researchers measured the potassium isotope compositions of Martian meteorites in order to estimate the presence, distribution, and abundance of volatile elements and compounds, including water on Mars, finding that Mars has lost more potassium than Earth, but retained more potassium than the Moon or the asteroid 4 Vesta. This suggests that the rocky planets with larger mass retain more of the volatile elements during planetary formation, and that Mars and planets that are similar to Mars outside of our solar system would fall below the size threshold necessary to retain enough water to enable habitability and also plate tectonics. So that's really interesting. So this suggests that Mars might just be too small, or rather would be too light, not have enough mass to have enough gravity to actually retain enough water to support life. So as the article observes, obviously water is essential for life on Earth and other planets. And there's evidence that Mars has had water in the past, but most of it seems to be gone. And so the idea is when we use the term volatile, we're talking about the propensity of certain compounds and elements to go into the gas phase and then leave. And, the gravity of the planet is going to have a lot to do with whether or not that happens. So we say that remote sensing studies and analyses of Martian meteorites dating back to the 1980s posit that Mars was once water-rich compared with Earth. And more recently, the Curiosity and Perseverance rovers on the ground returned dramatic images of Martian landscapes marked by river valleys and flood channels. Despite this evidence, no liquid water remains on the surface. Researchers propose many possible explanations, including the weakening of Mars' magnetic field that could have resulted in the loss of a thick atmosphere, because the magnetic field of a planet can help shield it from bombardment from solar energy that can basically help or essentially strip away the atmosphere of a planet. But a study published the week of September 20 in the Proceedings of the National Academy of Sciences suggests a more fundamental reason why today's Mars looks so drastically different from the blue marble of Earth. And they say that Mars' fate was decided from the beginning. So basically, just because of the fundamentals of gravity and the size of Mars, the supposition is that Mars was never really going to be able to retain water long term. So this has some implications also for the long-distance future for astronomers in their search for habitable exoplanets and other solar systems, which is to say planets and planets and other solar systems. And Wang now thinks that for planets that are within habitable zones, which is the sweet spot between where you're not too far from the star and not too close to the star for life, planetary size should probably be more emphasized and routinely considered when thinking about whether an exoplanet could support life. So for the next article that I want to talk about, this one is from phys.org, and it says, pinpointing the role of climate change in every storm is impossible and a luxury most countries can't afford. And so you've probably seen in all kinds of news articles and things like that, whenever there's a hurricane or storm, or really any kind of extreme weather event, there will be some headline that says, climate change was the reason for the storm, or climate change contributed to it, or just suggests that it's due to climate change. But this article proposes that this is maybe not such an easy inference to make. So it says, Tropical Storm Ida recently left a path of devastation across the U.S., and the inevitable question after each of these extreme weather events is the same. To what extent did climate change make it worse? So the article says, this is normally where the science of extreme event attribution steps in and identifies whether and to what extent human-caused climate change altered the likelihood and intensity of the event. Event attribution studies have delivered clear results partly as the methods and models that scientists use have improved, but mostly because the signal of climate change is becoming clearer with every extra ton of carbon dioxide emitted into the atmosphere. The added value of attribution science is taking the default answer of climate scientists that extreme events are something we expect to see more of in a warmer world and wrapping numbers around these changes. I'm going to be honest here, I don't really think that this is a legitimate scientific discipline. The reason being is what they're doing is they're saying that, like most scientific questions or problems, you're taking observable phenomena and you're drawing causative or correlative relationships between them, but you always need to have a strong control group of some kind or some sort of baseline to compare to. And though I haven't gone through their specific methods and models, it seems like a very, very sticky question to actually untangle. Because in order to actually determine whether a extreme event is due to a specific variable like increased carbon dioxide in the atmosphere, you would first have to determine what is the baseline for an extreme event to be considered an extreme event. And to do that, you actually have to have a very, very big data set, because the thing about extreme events is that they tend to be more rare. And so that actually falls under a type of mathematics that you would consider to be statistics related to fat tails, which is to say things that happen in several standard deviations away from a mean. And the nature of those events is that they're rare. So to determine whether a rare event, or we'll say an extreme and rare event, is actually extreme or rare compared to other extreme events, you would need a very, very long weather record. So the other article that I want to talk about today is from phys.org, and it's called Solar Electric Propulsion Makes NASA's Psyche Spacecraft Go. This is a really cool article, and it made me really excited when I read it, and I'm happy to share it with you today. So when it comes time for NASA's Psyche spacecraft to power itself through deep space, it'll be more brain than brawn that does the work. Once the stuff of science fiction, the efficient and quiet power of electric propulsion will provide the force that propels the Psyche spacecraft all the way to the main asteroid belt between Mars and Jupiter. They're targeting a metal-rich asteroid also called Psyche. So they say the spacecraft will launch in August 2022 and travel about 1.5 billion miles. Once in orbit, the mission team will use the payload of science instruments to investigate what this unique target, that is the asteroid, can reveal about the formation of rocky planets like Earth. So this is very cool. So the spacecraft will rely on the large chemical rocket engines of the Falcon Heavy launch vehicle to blast off the launch pad and escape the Earth's gravity, but the rest of the journey, once Psyche separates from the launch vehicle, will rely on solar electric propulsion. So basically, they're going to have large solar arrays that convert sunlight into electricity, and this will provide the power for the spacecraft's thrusters. They're known as Hall thrusters, and the Psyche spacecraft will be the first to use them beyond the orbit of our moon. For a propellant, Psyche will carry tanks full of xenon, the same neutral gas used in car headlights and plasma TVs. The spacecraft's thrusters will use electromagnetic fields to accelerate and expel charged atoms or ions of that xenon. And they'll basically be emitting blue beams of ionized xenon. And this is so cool. It says in fact, the thrust is so gentle, it exerts about the same amount of pressure you'd feel holding 3 quarters in your hand. But it's enough to accelerate Psyche through deep space, and the spacecraft will eventually accelerate to speeds up to 200,000 miles per hour. So I think that's really neat. I just wanted to share that. I'm excited about the development of new methods for traveling in deep space, and I think that it's an exciting development that they're going to go to this asteroid and see what they can find out there. So thanks again for watching. This has been another Science Update. I hope you'll join me again in the future, maybe tomorrow. Bye.